All right, let's do this. So today's the LO3 lab review. My plan is to go over two memory diagrams, judging by what we did in the last lecture. I won't be sad if we don't get to the tree example, and we won't get to it just based off what happened last lecture. We got through the first two questions, but we won't be able to get through all two. I only have 1 hour instead of 2 hours, what these usually take. But we'll get through the first two questions. The tree, though, it's almost identical to the example I gave in lecture, so you can follow that lecture. I don't remember if I said it in this section, but there was a small miscommunication between me and the TAs where this tree should have been a little bit smaller. We ended up with a tree as big as the one I showed in lecture, but actually one node less, right? Which is a little bit extra tedium that I didn't really want to make you go through, but it's perfectly, it's fine. It was just a little extra writing. But I wanted to mention that just in case anybody's interested. But what we can get through is Q1 and Q2. Before we get into that, anybody have any general questions? Perfect. So as far as grades for the quiz and interview, if you're in a Tuesday or Wednesday lab, they should be released. I did have one student in the last lecture say they were in a Wednesday lab and haven't gotten theirs yet, that I'm going to look into that once I'm done for the day, probably tonight, and make sure that those are out. The interview grades, the grades were posted to Autolab over the weekend, but the TA, simple mistake, but just forgot to click the release grades button. So I did click that an hour ago, right before the last lecture, during the beginning of the lecture. So grades are released. If you didn't see your interview grade and you're in a Tuesday or Wednesday lab, go to Autolab, click refresh. You should be able to see your results from the LO3 interview from last week. We want to get grades out as quick as possible this week because you have to make a decision, like how am I going to allocate my study time? Do I need to prepare for the quiz, the interview? What do I need to do? So we're trying to get them out pretty quick. We should have all grades released, including the Thursday and Friday labs, by tomorrow. So you'll at least have a day or two to look those over and think about what you have to review. No questions? Okay. So we want to do Q1 and Q2. I want to get through these linked list ones. These are the bulk of the quiz. Is that fair? I mean, in terms of number of questions, it is. I think it's the... We're just going to do Q1 and Q2. I don't have a good intro for you, sorry. All right, so this is one of the tougher lectures logistically, just because I want to show you this code, but I'm going to go to the document viewer and I'm actually going to do the quiz by hand with one of these old-fashioned things, the way you all have to do the quizzes. This is the only time all semester where I'll actually do the quiz on paper. You'll figure out very quickly why I don't do this often, my handwriting, my organization. I might get it a little better just because I had an hour of practice right before this. But the organization is pretty bad. I like the slides because they keep me nice and organized and hitting the points that I want to make sure that I hit with everyone without making mistakes. So if I do make mistakes, hopefully I can catch them all, but if I don't, y'all can help me out and point out what I missed. So for the logistics, I took pictures of these. I'm going to go over the same questions that I just did in the previous lecture. I posted images of both the questions in the lecture channel of the Discord. So if you can go in the chat and see those pictures so you can follow along with what I'm doing in the code. If for whatever reason you can't access that or whatever, and you're losing track of things, feel free to just let me know. I'll switch back to my laptop and then show the code a little bit, and then go back to the document viewer. So that's my plan. This first one, we're creating a linked list and then calling this multiply method. Let's get into it. And you can see, in case you ever thought I was lying, I just have Discord open on my phone all the time during lectures. All right, so let's start a memory diagram. I can zoom in a little more than that. Get right to the top of the page and start a memory diagram. So we want to start with our stack and heap. Not the pen I was just using. We want to start with our stack. Ooh, that's much better. Stack and heap. And further, I want to divide the stack into name and value. Hopefully everyone's familiar with that part, or else you're in quite a bit of trouble. I assume everyone's good with this. And let me, way down in the corner, put my I/O somewhere in here where I know I'll have room. I should have room here. I jumbled things up in the last lecture and had my objects going around my I/O content, but we'll get it this time. Let's just start this thing. So let me organize this a little better. So to start off, we have var double L of type linked list node of int equals new linked list node of 2 and null. So we have a constructor call here. We see the keyword new. We know we're creating a new object. The result is going to go into a variable named double. Oh my goodness. We'll get through this. We can do this. I'm starting over. Double L. I always have bad handwriting, but the extra pressure of having people watch you write is, and knowing you can see my hands too. It's pressure. So double L is going to get the value that's the return of this constructor call. The constructor call is a stack frame. The stack frame, and I'm going to abbreviate linked list node to LL node. If any TA gives you trouble for abbreviating something like that, let me know and I'll give you whatever points you lost for that. If you ever lose points for abbreviating, something that's very clear. LL node, everybody on the planet is going to know, at least every TA is going to know that that means linked list node, and that you just didn't feel like typing linked list node. The return arrow is going to go into double L. In the other lecture, my laptop was to my left, so I got to flip my brain around here. And the parameter, the constructor parameters are named value and next. And since it's a constructor call, it's a method that's defined within a class, we're always going to have this as one of the constructor parameters. This is a reference to the object that's being created. So we're going to create a linked list node. Again, I'm abbreviating LL node, and we need to come up with some reference number. For some reason, I always start with 200. I don't know why. But I'm going to give this the reference 200. So this, a reference to the object that's being created, OX200. And our value is 3. No, our value is 2. I got this. And then next is null. So those we're just copying from the argument list when calling the constructor. Since these are constructor parameters, they automatically become state variables. So value, next, to null. And again, I've said this a lot throughout the semester, but I'm going to leave off my arrows just so things are a little clean. But when I start linking these nodes together and creating the linked list, I actually will end up drawing some of my arrows just to help me visualize what the linked list actually is. So all my nexts, I'm going to draw my arrows for those when we get there. But for this one, I'm not going to bother drawing my arrow. I'm going to double check and make sure, okay, this 200, node 200, make sure that those match exactly, and then I'm going to call that good. So this is going to return. By the way, this is all review for prepping you for lab this week, so if you do have questions, just stop me and let me know. Otherwise, I'm just going to rip through these memory diagrams. I'm going to get a little bit on autopilot, so slow me down, stop me if you have specific things you want me to say. Constructor returns, especially creating these linked lists. It gets a little repetitive, so I'm just going in autopilot for these ones. Let me know if there's something specific you want me to clarify that wasn't 100% clear. So I'm going to return that. Double L gets the reference 200. We're going to create another linked list node. We have a constructor call that's going to return to double L, LL node. This value next. I'm going to create a new linked list node. Never leave myself enough space. New linked list node. I'm going to give it a reference, OX about 505. Value next. So this is going to be whatever reference number I chose. Again, we're making these up. You all know that by now. OX 505. And value and next are going to be 3. And our first thing where we have to check just a little bit, next is going to be double L. And it's very important to keep track of these when you're creating your linked list nodes, to see if we're prepending, if we're appending, if we're adding nodes to the middle of the linked list, like we will in the next one, what this is. With the memory diagram, and the theme of my example today is going to be, we don't really have to think about it at all. Double L. Next is double L. We're just going to look. What's the value of double L? OX 200. Sometimes with these memory diagrams, the less you think and the more you act like a machine, because that's what we're doing with these memory diagrams. We're being the computer and reading and running your code. The computer doesn't think at all. It's just blindly going step by step and looking up the values. When it gets a variable name like double L, it just looks up on the stack and says, what's the value of double L? Okay, oh, here's a double L. Oh, it's OX 200. And then just using OX 200. Not really thinking about what the program is doing. Throughout this whole thing, I'm not going to think about what this program is doing. I'm just blindly going line by line and manipulating what memory has to change. So this 505 value 3, next is OX 200. Our constructor parameters automatically become state variables. This returns, a constructor returns a reference to the object that was created. I'm going to go up first because I know I'm going to have to replace this a few times. So OX, I would prefer not to do that, but they'll be fine. That'll be fine on your quiz, as long as you have the right values crossed out. I'll draw a little arrow so the TA grading my quiz will know that I went that way, that I went up just in the name of space. Next line, we're going to create another linked list node. It's a little tedious, but if we want to test your ability to work with linked list nodes, very first thing we have to do is have you create a linked list. So we just need a linked list with enough nodes to make things interesting. This value next. We're going to create a new linked list node. Value next. And OX about 101. Oh, I got the repeating numbers again. This OX 101. Oh, and I said I was going to do it, and then I didn't do it. Next, I do want to actually draw these reference arrows just to help me visualize the list. I'm going to be careful with those, as we'll see in the next one, because if I know that arrow is going to be replaced, I don't want to be scribbling out arrows, because then it defeats my readability. This is 4 double L, 4, and next is double L. I'm not thinking about what double L is or what this linked list looks like or anything. I am a little bit over here, but I'm just going to look at double L has the value OX 505. And then my thought process stops. I got the value I needed. I'm not going to think about it anymore. Copy those over to the state variables of the same name. Returns. This becomes OX101. I'm going to stick with my arrows there. And one more. Let's do this one more time. LL node, return arrow, which gets a bit messy. This value next. I need a new linked list node, so I have the value of this that I make up. I feel like I use 96 a lot too. Value next. This OX896. 5. And again, next is double L, which is currently OX101. OX101. And since this is my last node, I can draw the rest of my arrows here. So at this point, I can see that I have a linked list. Oh, one more step before I start talking about that. This returns a reference to the object that was created, and we're left with OX896, whatever the last number I made up was, as double L. So double L is a reference to this linked list node containing the value 5. Its next is 101, containing the value 4, dot next, 3, next, 2, next is null. So I have the linked list 5, 4, 3, 2, after all this, what ended up being pre-pending to the list. So we didn't think about, okay, we're creating a linked list, we're pre-pending. We didn't even use that word, except in my explanations of it. But when we're doing our memory diagram, we just follow the references, look at the code, figure out what's being asked for, what values are going where, what references are going where, and then just writing them down and just being very methodical, very attentive to all the details as we're going through this step by step. Again, just like the computer is when it runs your code. Okay, and next, we have a variable x, which is going to get the return value of a method named multiply. I don't really have a great way. I guess I could just do mult. I guess that would be clear to any TA grading my quiz, to shorten multiply. Multiply is going to take two parameters, one named LL and one named total. Does everyone have the picture? Anyone want me to switch back to the code for a second? Everyone good? You have the pictures in the Discord? What's that? You're good, or you want to see it? Good? Okay. I just want to make sure everyone can follow along with it. So we're going to call multiply. It's going to have two parameters. Oh, yeah, that's what I was saying. So since multiply is a method defined in an object, it's just a method we're calling for some functionality and its return value, I'm not going to worry about putting this and then a reference for this specific method call. Whenever it's a method or a constructor defined in a class, then we're always going to put the reference this, which is a reference to either the object being created or the object that called the method. If it's defined in an object, like this is object Q1A, we're not worrying about the reference to an object. Technically, there is one. Whenever you run the debugger, you can always see that reference in there. And if you do add that, and add it properly, I should say, if you add that properly, no one's going to hold that against you. The TAs are going to be fine with that. I'll be fine with it. Because it is there technically. We just don't worry about it in our memory diagrams because it's not useful, it's not relevant information to what we're doing. If you did do that and you put on your heap, like if over here on the heap, I created an object named QA1 with no state variables, gave it a reference number, and then put this right here, which is a reference number to that object Q1A. That'd be accurate, that'd be fine, all that would be fine. But for our memory diagrams, it's optional and even a little discouraged because it's just extra clutter in your memory diagram that isn't relevant to the code that's executing. If object Q1A had state variables, then it'd be a different story, but we're not putting state variables in objects. I did that once all semester, and it was just to motivate classes where we're actually using state variables. Using state variables in objects is awful. It's just a bad idea. Not to go too far down this rabbit hole, but putting state variables in objects is effectively having singletons of those variables, which is almost as bad as having global variables. You can only have one copy of those variables ever, which is a bad idea. At some point, you might decide that you want multiple copies of those variables, in which case you should just have a class instead of an object. So I said I don't want to go down that rabbit hole. We're not going further down that rabbit hole. All right, so we have a variable x, which is going to be assigned the result of this multiply method call. Multiply has parameters LL and total, so I'm getting my parameter names on here first. I've said this throughout the semester too. The order in which you draw things, you might notice that I'm writing things down in a different order than you might have. That's perfectly fine. As long as the final memory diagram is the same, that's what we're looking for, because that's the only thing we can grade anyway. We're not watching you do the quiz and seeing if you did things in a certain order. And there really is no right or wrong order. Technically, there is an order that the computer's going to read these things in, but I don't care. So LL is going to be the value double L. And again, I'm not thinking about this too much. I'm just looking. What's double L? It's the reference OX896. OX896. And then total is initialized to 1. When this method is called, it's going to check if LL node equal null. LL node dot next equal null. I don't think so. That don't look like null. So I'm going to hit the else. I can see in the if and in the else that I'm not declaring any variables in either of them. So I'm not going to worry about my dashed boxes. We only have to draw the dashed boxes if you're declaring variables inside the box. So technically, I could have an empty dashed box here. An empty dashed box would be fine. You're not going to lose points for that. Or not points. We don't have points in this class. But it's not going to be held against you at all. Technically, there's an empty box there. If it's empty, we don't have to draw it. We're going to leave that as optional. So we hit the else. No variables declared, so nothing to worry about with code blocks and scoping and all that stuff. But we are going to make a recursive call to multiply. Now, recursive calls on our memory diagrams, we're not going to overthink them at all. I'm just going to treat it like a method call, just any other method call. I have a method call called for multiply. I'm going to create a stack frame for multiply. I think memory diagrams it's one thing that can really make recursion make more sense, is going through a few memory diagrams with recursion. I call multiply again, so I put a stack frame on the stack. ll.next, ll.next. Oops, let me get my names on here too. LL and total. LL is ll.next, OX101. And again, I'm not thinking about it too hard. I just see ll.next has to be resolved. That expression has to be resolved. Well, what's LL? It's OX896, and there's a dot. Dot is going to mean follow the reference to the appropriate object that it refers to, and then next. What's the value sitting next to the variable name next? It's OX101. So that resolves to OX101. Yeah. So stack frames are completely independent environments from each other. So to reflect that in our memory diagrams, we draw them as completely separate instead of inside. Because there's no code blocks, we would draw them inside because there are scoping rules, and you can break outside of a code block and find variables that are outside that code block, but you can never break outside of the stack frame. So that's why we always draw them below. So it's a subtlety, but that's why we do that. And then total is going to be total times LL dot value. Total times LL dot value. 1 times 5. If my math is right, it's 5. And then in this recursive call, we have our parameters assigned to the argument, or the arguments assigned to the parameters, and we're going to start executing code. If LL.next equals null. LL.next doesn't look like null to me, so we're going to hit the else, which is making another recursive call to multiply. Multiply. Oops. My return arrow for recursion, we just draw it to the previous stack frame. Yeah, my flag. Make sure you point that out, Weird Alex. Weird Alex, you're not even in the room, are you? Yeah, I had my flash on, but the flash didn't happen to cover up any important code, so whatever. I just left it. LL and total. LL is going to be the LL from the previous stack frame dot next. So LL dot next, OX505. In this stack frame, we're making the recursive call to this stack frame. So when we're making that recursive call and resolving the arguments, we're using this LL in total. So LL.next is the new LL, and then the new total is total times LL.value. 5 times LL.value, 4. So 5 times 4 gives us 20. Then in this stack frame, we start executing code. If LL.next equals null, LL.next is not null. So we're going to hit the else, which makes another recursive call. We have to resolve the arguments so we can get our parameters again. Multiply. LL total. LL.next, OX200. And total is going to be total times LL dot value 3. 20 times 3 gives us 60. And now LL, we're going to start executing code in this stack frame. This is where we get a little tricky on you. LL, if LL dot next equals null, LL dot next does equal null. So we just return total. This stack frame returns 60 to this stack frame, which was just waiting for its return value from this stack frame so it can return it. Technically, this is tail recursion, but we always draw all of our stack frames as though it were not in our memory diagrams. So this returns 60, returns 60, returns 60, and we get 60. Then the last line, don't forget your I.O. Make sure you get your 60. Forgetting the I.O. is alone wouldn't be the biggest mistake, but if you have that compounded with a few other little mistakes, it could be the thing that pushes you over the edge. It makes you have to retake the thing. So don't forget your I.O. So this is where things get a little tricky on this one. And I like these kinds of questions because if you're just looking at the code and trying to comprehend what the code does, you might want to say that the answer is 120. You're multiplying all the values in the linked list. That's going to be 120 if you multiply all these things together. But the way the code is written, if you're just blindly following the code, which you should be doing for a memory diagram, and just going line by line like a zero IQ computer and figuring out, okay, what are the values going to be, and just very meticulously, very attentive to all the details going through this thing, you're going to notice that we never get this multiplied by 2. That last node of the linked list is never actually multiplied to the running total. So that's something that if you're going through the memory diagram, you're going to be able to, bless you, you're going to be able to see that pretty easily. You're just not going to multiply by that 2 because dot next was null, so you just don't multiply the times 2. But if you're trying to like game the system and try to reverse engineer the question of what we're asking, you're going to have a 120 there, and it's an easy thing. It's an easy scan during grading. If IO has a 120 sitting there, we know what to look for because we know you did something that you weren't supposed to do. It helps us during grading. If you got a 120, you definitely did something wrong, and we just got to see what it was and then mark that down. Because we like to trick you with the names. It doesn't actually multiply all the values. Sometimes it does. So this should be if LL, I'm trying to point, but I don't have the code up. So it should be if LL dot, it says LL dot next equal null. It should say if LL equals null. Then just return the total. Because that means you already went past the last node and you have an LL of null. But just checking LL.next equals null, this skips the last node. Okay. Any questions on that one? And more importantly, did I miss anything? I think I got everything on this. I think everything's fine. It's a fairly straightforward create a linked list and then navigate the linked list to do a little bit of computation using some recursion. Which is, when I say it out loud like that, it's a lot, but at this point in the semester, at this point in your careers, this should be no big deal for you. So if there is a big deal, I want your questions. This whole thing is to help you with this week's lab, so I want your questions. Yeah? Yeah, so with this setup, I'm trying to point to the code again. So with this setup of the recursion, you'd have to say if LL equal null, and that would get you through the whole list, and that would return 120. But this one, if LL.next equal null, we never actually process the last node's value. The node with a next equal to null, we never access its value at all. Because if we're at the last node, we just return total, but we never get LL.value if it's the last node. So alternatively, we can return total times LL.value right here, and that would give us the same thing. But it's a little redundant code. I would prefer LL equal null, because that means we already processed the last node. We made a recursive call for its next. Its next was null, so now we're past the end of the list. There's nothing else to do, and then just return total. Could you review the binary tree question? I mean, I don't have intentions to because I want to do this linked list one because this one throws some tricks at you. Maybe I'll talk about the tree a little bit. I don't know. I don't really want to do the tree because I did almost this exact, I think I did post-order traversal and this is an in-order traversal. But I did the exact same thing in lecture with a memory diagram. It's a lot of writing null and a lot of stack frames. So I'd refer you to that lecture, unless you have a specific question. If there's something specific you want me to talk about with the tree example, I can do that. But I don't want to go through the whole example because it's just exactly what I've done before in the past. Yeah? Can you just go through like that? So when we call this on tree, at this point tree is going to be, I'll try to do this quickly without doing a memory diagram. So tree is going to be 2, tree.left is 3, tree.right is 4, tree.left.left is 5, tree.left.right is 10, tree.right.left is 9, and tree.right.right is 6. And then we're calling traversal on tree. So when we call this on the root node, we're checking if the node is not null, which it's not, it's an actual node, then we're going to make a recursive call on its left child. So we have one stack frame here, which is going to recursively call itself over here, which is going to recursively call itself on the left, which these all have nulls, which is going to recursively call itself, its left child. It's going to recursively call traversal on its left child as the parameter. And at this point, we finally get node equals null. So this returns, goes up to this node, which is going to print its value. We're going to print 5. And then make its right recursive call. Make a recursive call over here. That has nothing to do because it's null. And it returns, goes up here, prints 3, and then makes the right recursive call and keeps going that way with recursion. So we're going to navigate this whole tree going here, 3, 10, 2, 4, 9, 4, 6, and then return, and then finally return up the recursion after visiting every node. Does that help? Yeah. Cool. At some point, one hint, if you're doing the traversal right, if it's this big of a tree with size 7, fully balanced like this, 1, 2, 3, 4, 5, 6, 7, 8, you're going to have 8 stack frames with just node equals null. And this is a method defined inside an object, so we wouldn't have this in any of the stack frames. We would just have node. Each one of those stack frames is just going to have a reference to the node that's being used for that stack frame. Any other questions on the tree? Because I want to switch back to the second linked list question. Good? Any questions on anything else? Everyone has a question of the, let me show the code just in case, just to refresh if you're not looking at the picture. But we want to create a linked list node, but we got a little twist in the middle, or a linked list. We want to create a linked list using nodes. Got a little twist in the middle, and then we're going to call this sum method using recursion again. Let's do this. Okay, I'll try to go quick through the first part. Again, if we want to ask you questions about linked lists in memory, we have to have you create a linked list first. So stack, heap, name, value. So I'll try to rip through actually creating this stuff. Oops, that was not a straight line. Double L equals a new linked list node of 9 null. LL node, return arrow goes here. This value next is going to be a linked list node with value next and a reference. And I'm going to get ahead of myself just a little bit on this one to organize my heap a little bit. I see that I have the keyword new 5 times, and none of them are in loops or conditionals or anything. I'm going to end up creating 5 linked list nodes. So I'm just going to set up my heap to have those 5 linked list nodes to help streamline things when I'm talking about this stuff. So I have another linked list node. Value next. OX, about 501. Another, bless you, another linked list node. Value next. OX 450. LL node 1, 2, 3. Oh my goodness, I got 2 more of these to write. Value next. OX 005. LL node value next OX 001, because why not? Then I know where I have room for my IO. All right, so the first linked list node is going to be 9 null. Well, first we have our random numbers already chosen, OX999. Happens to get a fourth 9, null. 9, null. OX999. Stack frame returns. We get another linked list node. Going to return in double L. This value next. This is I'm going to use my 501 that I set up. 501 value 5. Next is double L, OX999. 5, OX999, which refers to this guy. Returns, OX501. Another one of these, LL node. Returns to double L, this value next. This, I'm going to use my 450, OX 450. Value 3, sideways. Value 3, next is double L, which is 501 at this point. So again, I'm just looking at what values. See, I almost wrote the wrong number. Since I'm skipping my arrows, I had the wrong number there. That would have been bad because it's not clear that I know what I'm doing at that point. So 450, 3, OX 501. This returns, and this gets OX 450. So again, I'm just blindly looking. Okay, next is double L. What's double L at this very moment? That's what next is at this moment. I'm not looking at this and thinking, okay, it looks like I'm pre-pending or maybe I'm up. I'm not thinking at all about that. I'm just looking at each constructor call. Each constructor call takes double L. What's double L on my stack at this moment? That's what next is for that node that's being created. Sometimes it helps to think less on these memory diagrams. Don't use it as an excuse. I know I failed, but you told me to think less. But hopefully you get what I'm saying when I say that. Think like a computer. Very meticulous, but not thinking very deep. New double L. So we're going to create a new variable, new double L, and assign it the value of double L. Now again, when we're assigning a value from one variable to another variable, we're just straight up looking at the stack. What's the value of double L? It's 450. That's it. That's the assignment. We're not creating a new linked list node. We're not creating a copy of a linked list node. We're just copying whatever's sitting in the value column next to the variable of the name that we're looking for. That's it. So we copy that value 450. Double L and new double L are both referring to the same object on the heap. And then the twist, new double L dot next equals null. New double L dot next equals null. And I thought I had a little bit, just because I'm drawing my arrows like this. I purposely didn't draw this arrow because I knew it was about to be severed. So once we change that, new double L and double L both refer to 450. 450 has a next of null. Those are the only linked list nodes that we have access to. At this point, what we've effectively done is severed our connections to 501 and 999. This linked list of size 2, it still exists in memory at the moment anyway, But we have no way to access it, and it's a candidate for a garbage collection. These two nodes are going to get garbage collected. They effectively don't exist to us, and pretty soon they won't exist at all. Yeah? So we're going to new double L dot next equals null. So we went new double L dot, and then next, we're changing the value stored in this variable to null. So we just changed that from a reference to 501 to null. But we never actually went to 501 and said this whole node is null. We didn't mess with that at all. We just said 450's dot next equals null. We never had a dot after that next. So every time we see, oh, go ahead. Yep, so every time we have the dot operator, we're going from a reference, not strictly speaking every single time, could be a method call, but when we have the dot operator, we're going from a reference to the object that it's referring to. So we would say, we're saying dot next, we're saying new double dot, that means head over to the heap where that object that this reference refers to is located. And then we're saying next, we're just messing with this variable. If we wanted to go to 501, we would say dot again, travel to this reference, and then start messing with this node here. And then we could change its value in next to null if we wanted to. But we actually don't have a mechanism to just wipe out a whole object. We can't just say this object, get rid of it, and change it to null. But we can change the reference that's stored in a variable, which is what we're doing. The only way to get rid of an object is in Scala, I should mention, and JVM languages, is to do what we just did, sever ties to these. We have no access to these, so then the garbage collector is going to reclaim that memory and get rid of those things. Bless you. And in our memory diagrams, we're not going to worry about garbage collection. Maybe next semester, maybe sometime in the future, shortly, we'll start doing that. But this semester, we're not worrying about garbage collection. All right. Oh, no, we don't have much time. Let's at least try to get the linked list created. It looks like we're not going to get to the recursion on this one. The recursion works the same way as the last time, though. So the big thing that I have to say about the recursion, I'll try to explain it while I'm finishing up the list, is that, and this was a common mistake that we saw in the LO2 quiz, when a method is inside a print line, don't forget to add the stack frames for that method call. So we have print line of sum of new double L of 0 and 0. That sum method and all of its recursive calls, bless you, and all of its recursive calls, you have to write those stack frames. You have to go through all that in your memory diagram. If it's just like print line X like we had in the previous example, that you don't have to put on there because you don't have to put the actual stack frame for print line on your memory diagram because it's internal to Scala. But the sum method, you have access to the code. It's right there on your quiz. You do have to add that stack frame. So don't forget to add those stack frames on your quizzes. This one, 005 we're using. Value 4. And next equals new double L, which is OX450. That returns. And then one more, we'll at least get to finish creating this linked list. This value next, 001, 2, 005, 2, 005, returns 001, and then we would have some node total, ... et cetera, et cetera. So we didn't get to finish this one, but it's fine. The next is the recursive call, and then printing. Don't forget to print to the screen your value. But what we have effectively are two linked lists. This one of 3, that's what we're referring to. That's what we're going to go down the recursion with. And then this one that we don't have any ties to. And double L still just refers to this single node that has the next of null. I'm out of time, so have a great day. I'll see you all Wednesday.